Hello everyone. In the last video that we looked at together, we learned how to simplify radical expressions. We're going to take that a little bit further this time and learn how to actually combine radical expressions. And combining is a general word for adding and or subtracting radical expressions. So, for example, if you have a situation where you're combining two expressions such as 2 radical 3 plus 3 radical 3, the important thing that we're going to want to look out for is that the radical part be the same. In that way we can kind of like factor it out and get 2 plus 3 times radical 3 by just factoring out that radical 3, and we end up with 5 radical 3. So just like the process of combining like terms, notice we usually don't show this step and we usually just jump from here right to there. But just so you know, the reason that it works, it's because we are doing that kind of factoring. Or you could have cube roots. It'll work out the same way. Let's say we have the cube root of 2xy plus 6 cube root of 2xy minus 11 times the cube root of 2xy. The fact that all these radical parts are the same tells us these are like terms, so we can go ahead and combine them. Notice that counts as 1, so we have 1 plus 6, which is 7, minus 11, so we end up with negative 4 times the cube root of 2xy. Now, sometimes we may encounter a situation where it doesn't look like we have like terms, such as square root of 50 plus the square root of 32. On the surface, it doesn't appear like we have like terms, but if we delve a little deeper with the methods we learned last time, we know that we can write the square root of 50 as the square root of 25 times the square root of 2, and we can write the square root of 32 as the square root of 16 times the square root of 2. Now notice that the square root of 25 is just 5, so we get 5 radical 2 plus 4 radical 2, and now we have like terms which we can combine, and we end up with 9 radical 2. So sometimes we have to do a little bit of work before we discover our like terms. Make sure you understand that before we proceed. So here we have another situation where we will want to do some simplifying first, and using the methods of simplifying radicals, we go ahead and break up each of these radicals into two parts. And in one radical we put in this case the index is 2, so we put the perfect squares in one and the non-perfect squares in the other radical, as far as we mean the factors of that original expression. So for the first expression 20, if we break it down using prime factorization, we have 2 goes into it 10 times, another 2 5 times, and finally 5 goes into it once. So we have a perfect square of 2 squared or 4. We can put 2 squared or 4, makes no difference, and we're left with a 5 which goes in the other radical, the non-perfect square group. And in the as far as the x squared is concerned, all of it is a perfect square, so that will go in here. For the other term, we have negative 5x, and then we just need to simplify the square root of 45, and we know that 3 goes into 45 15 times, 3 goes again into 15 5 times, and 5 gives us 1. So we have a perfect square which is 3 squared, which we can put in the perfect square radical, and we're left with this 5 which we're going to put in the non-perfect square radical. So now we notice that we have 2x radical 5, because remember the square root of 2 squared is 2, the square root of x squared is x, the radical 5 just comes down, minus 5x times 3 radical 5. Simplifying a bit further, we end up with 2x radical 5 minus, we can multiply the 5 and the 3 to get 15x radical 5. So what makes these two terms like terms is this part of each. So those are what we're combining. So we have 2 of those minus 15 of those, so we end up with negative 13 of those objects, which are x radical 15. And that's how you simplify those. Try to do write the problem down, see if you can do it on your own before you continue. Okay, so here we have another problem we can approach. I think you should be able to do this on your own, so definitely try to do so before you come back. All right, so here we're gonna simplify each of these radicals by breaking them into two parts, the perfect square part and the non-perfect square part. And of course we would not need to do that if any of these radicands was already a perfect square. We would just calculate what the square root is, but since none of them are, we are going to have to break them down, and we'll do so with each of them. So remember, in each part we're going to break him up into a perfect square radical and a non-perfect square radical for each of those original radicals. All right, and so for the first one we have 75. If we break down 75, we notice that 7 plus 5 is 12, so 3 goes into it, so we start with 3. We always want to start with the smallest prime number to get a nice ordered group of prime numbers here. 3 goes into 75 25 times, then 3 doesn't work anymore because 2 plus 5 is 7, which is not divisible by 3. So we'll go to 5. That gives us 5. Finally, 5 goes into itself one time. So we do have a perfect square here. We're going to put the 5 squared in here, and we have 3 left, which goes into the non-perfect square radical. So next we'll find the prime factorization of 200. With that one we start with 2, which gives us 100. 2 goes into 100 again 50 times, and 2 goes into 50 25 times, and then we have 5, which gives us 5, and another 5 gives us 1. So we have 2 perfect squares in the factorization of 200, which can go into this box, and we're left with 1 2 here, which goes there. So notice here we were just finding the simplified version of 3 radical 200. Now we're moving to this one. So we're going to find the prime factorization of 45, which gives us 3 15. Another 3 gives us 5, and 5 gives us 1. So we can see there's a 3 squared hidden in there. We put that in the perfect square box, and we're left with a 5. That's going to go into the non-perfect square box. Now we're working on the last one, 3 radical 27, which we're going to put in here. So if we find the factorization of 27, that's simple enough. 3 9 3 3 3 1. So we have a perfect square right there, which is 3 squared, and we have 1 3 that's by itself, so that's going to go into the non-perfect square part of 27. So now we realize that starting here, the square root of 5 squared is 5, so we get 5 radical 3 minus 3 times, we know that the square root of 2 squared is 2, and the square root of 5 squared is 5, so we're going to get times 2 times 5 radical 2 minus 7 times 3 radical 5, and then plus 3 times 3 radical 3. So now we're just going to clean that up a bit. So we get 5 radical 3 minus 3 times 2 is 6 times 5 is 30 radical 2 minus 21 radical 5 plus 9 radical 3. So we notice that we only have two like terms here that can be combined, right there and right there. So when we combine those, we end up with 14 radical 3 minus 30 radical 2 will just come over without change, as will negative 21 radical 5. And that is all we can do. This is not going to simplify any further. So we just box it and we are finished with it. So again, please make sure you can do that on your own before you continue with the video. Okay, so let's bring in some variables here. And of course, as you know, the approach is exactly the same. We're going to break down each of these radicals into two parts. The perfect square part and the non-perfect square part. Now in this case, we can see no factor under this radical is a perfect square, so there's no need to break this in two parts. That one is just going to stay the same. The last one, there's something we can do, so we'll go ahead and break that up too. So we'll put the perfect square part in the first radical, the non-perfect square part in the next one, and the same with this last one over here. So now for the first one, square root of 50, we know that 25 is a perfect square factor of 50. In fact, it's the largest such factor, and 2 will go in here. For x cubed, we know that x squared is a perfect square part, and x will go in here. For y squared, we know all of it is a perfect square, so it should go in the first radical. The next one, there's nothing to do. In the last one, we notice that 8 has a perfect square factor of 4 as its largest perfect square factor, and leaves us 2 in the non-perfect square radical. X cubed, we know that x squared will go there and x will remain. Now, if we go ahead and simplify further, we end up with 5xy radical 2x plus 3xy radical 2xy minus the square root of 4x squared is going to be 2x. So 2xy radical 2x. Note if all three had ended up being square root of 2x, we would have been able to combine all of those. But as it stands, this one is not going to factor out along with these two. These two, however, there is something we can do. We notice that this portion of these two is exactly the same. So in fact, those two are like terms, and we can go ahead and combine those. And we're going to end up with 3. Let me go ahead and change my color. So we end up with 3xy radical 2x minus 3xy radical 2xy. I wanted you to see that even though this looks very tempting to combine those, you really cannot. The only other thing that sometimes you may see at the end of some sections, you know, when they give you the answers, they may factor out the 3xy and then just leave you what's left behind, which is square root of 2x minus square root of 2xy. And that's pretty much what we want to leave this as. So again, practice this, make sure you have it before we continue. Let's go ahead and take a look at one more problem of this kind with a different index, this time 3. So the approach is going to be exactly the same. We're going to go ahead and break each one of these cube roots into two parts. Of course, one part, the perfect cube part, and then the next part, the non-perfect cube part. So we'll do that with each and see what we end up with. So definitely try it on your own if you think you can manage it, and then come back. So 16, we'll break it down into 2, gives us 8, 2 gives us 4, 2 gives us 2, and then 2 gives us 1. So we notice there's a perfect cube hidden there. It's 2 cubed, and we right away take care of the 2 in the non-perfect cube radical so we don't forget it. As far as x to the 4 is concerned, remember that's just 4 factors of x, so obviously there's an x cube in there we can take out and put inside the perfect cube radical. That leaves us with 1 factor of x here, and y cubed is entirely a perfect cube, so we'll go ahead and bring all of that into the perfect cube radical. And that should be the end of this first term. For the next one, we have negative 7xy on the outside, and then 54, if we break it down, gives us 2, 27, 3, 9, 3, 3, and then 3, 1. So we have a perfect cube of 3. That leaves us a 2 as well, so we put the 2 in here. And there was already an x, which has to go into the non-perfect cube box because there is no perfect cube hidden inside it. So now, starting on the left here, we know that the cube root of 2 cube is 2, that of x cube is x, and the cube root of y cube is y. So we get 2xy times the cube root of 2x minus 7xy times 3 times the cube root of 2x. And of course, the first part we can't do anything with, we'll just rewrite it. It's 2xy, the cube root of 2x. Here we can go ahead and multiply the 7 and 3 to get minus 21xy times the cube root of 2x. Now we do notice that these two terms are like terms because that entire variable part is the same. So basically you have 2 apples, take away 21 apples, so you get negative 19 apples, with the apples this time being x, y times the cube root of 2x. So the exact same approach for higher level indices, and you just have to be careful to, when you do your prime factorizations, to look for perfect cubes instead of perfect squares. So go ahead and make sure you can try this and do this on your own before you continue for maximum benefit. Okay, next let's go ahead and take a look at a situation where we have some fractions involved. So I noticed that in the first fraction the denominator is a perfect square, so I think it would be beneficial for us to go ahead and break that down like this. That's going to simplify the denominator right away. In this next one, I noticed that we don't currently have any perfect squares, but I noticed that there's a common factor of 2. So if I were to actually do that simplification first, that would give us 16 and 25, which we now know that we notice is a much better situation for us, because we now can say 5 radical 50 over 5 minus 2 times radical 16 over radical 25. So here we can cancel the 5's to get radical 50 minus 2 times 4/5, and we end up with radical 50 minus 8/5, and radical 50 we can break up into radical 25 times radical 2 minus 8 over 5, and finally we have 5 radical 2 minus 8 over 5. Well, a lot of times we prefer to go ahead and combine those two fractions. So we in fact could have left this 5 down here, since we were going to eventually get a common denominator, but this doesn't matter. It's, either way will work. So now we'll go ahead and just get a common denominator of 5, which means we have to multiply the 1 by 5 and also do, of course, the same to the top. So we end up with 25 radical 2 minus 8 over 5. So that's how we can go ahead and tackle a problem like that. We'll do one more of these and then call it the day. But make sure you can handle this on your own before you come to the next problem. All right, so this will be the last problem we look at for today, just to bring in some cube roots. It looks like we have some perfect cubes on the bottom here, so let's go ahead and break these up into two radicals. We're using this rule which says the nth root of x over y equals the nth root of x over the nth root of y, as long as both nth roots are real numbers. So we get 5 times the cube root of 36 over the cube root of x to the 12 plus 3 times the cube root of 20 over the cube root of x to the 9. So now we're going to go ahead and get 5 times the cube root of, we can break that up. If you remember, 36 gives us 2, 18, 2, 9, 3, 3, 3, 1. And we try to see if there's a perfect cube in there. We don't find one, so we'll leave it as the cube root of 36. For the cube root of x to the 12, we get x to the 4. And we have plus 3 times, we know there is no cube root in 20, but just to show you, you notice that we have 2, 10, 2, 5, 5, 1. No perfect cube in this factorization either, so there's not much you can do with that either. So we get cube root of 20, and don't forget the 3 we already had there, over, we know the cube root of x to the 9 is x cubed, so we end up with 5 times the cube root of 36 over x to the 4 plus 3 times the cube root of 20 over x cubed. Now we can actually combine those into one fraction by finding the common denominator, which is simple enough here. It's going to be x to the 4. So this denominator is already x to the 4, so we don't do anything to that fraction. We get 5 times the cube root of 36 plus this denominator is x cubed. It's going to require an x factor, so we're going to go ahead and multiply the denominator and the numerator by x. So we're going to get 3x times the cube root of 20. So, and that's pretty much all that we can do here. All right, so just a little practice on how to combine these radical expressions, and next time we will look at multiplying and dividing more extensively when it comes to radical expressions. And we've only done it with one term so far. We're going to involve more than one term, and that's what we'll be discussing next time. So be safe until our next meeting.